Databases break reality, and ML engineers have to rebuild it. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry ready and apply your knowledge to real industry projects. So today we are taking a deep dive into the architecture of data and specifically how you take scattered information and actually turn it into something a machine learning model can understand.
Right, because there's this massive fundamental tension you run into when you start building real-world pipelines. Like, databases are designed entirely for storage efficiency.
Yeah, they take reality and they just completely shatter it into pieces. Right.
Exactly. I mean, you end up with a users table for who the user is, an orders table for what they bought, a sessions table for how they behaved, and maybe a products table for what was actually sold.
But a machine learning model, it can't learn from fragments. It needs the full picture.
It absolutely needs the full picture,
Yeah.
which is why today's mission is really to explore what we call the third SQL pattern, the joy.
The joy.
Yeah, we're going to look at how this specific tool is basically the ultimate mechanism to reconstruct reality for your models.
I mean, think about working with a database like dealing with a disassembled puzzle. Is that a fair way to look at it?
Oh, that's a perfect analogy.
Because the database just scatters all the pieces into these different little categorized boxes because that makes it incredibly fast to store and retrieve individual items. But your machine learning model is the person trying to actually solve the puzzle.
Right, and it can't just look at a pile of loose cardboard pieces.
Yeah.
It needs to see the completed box cover to make any sort of accurate predictions.
Exactly.
And the thing is, the database engine just does not care about the box cover. It separates those pieces because it's highly efficient for, standard software applications. Like if a user updates their password, the database only wants to touch the user's table.
It doesn't want to load everything else.
Right. It completely refuses to dig through millions of past orders or session logs just to update one single password. But from an ML perspective, that fragmentation is just a massive roadblock.
So by using a join, you're basically forcing the database to connect these isolated fragments to create what we'd call a complete feature view.
Yes. For example, combining the users table and the orders table reveals a user's spending behavior. Combining users and sessions reveals their activity patterns.
So visually, from an engineering standpoint, this moves you from a really narrow base table like maybe just a user ID and an age to a wide feature table by appending all these new columns.
Exactly. If we connect this to the bigger picture, you really have to understand why machine learning models fundamentally require this wide, flat matrix to function.
Right, because if you have some basic Python experience, you know that models under the hood are really just doing linear algebra.
Yeah, they expect a flat, two-dimensional array of data, which is often called a tensor. They just cannot dynamically read across multiple disconnected tables the way human intuition can.
I mean, a human can look at a user profile on one monitor and, an order history on another and just instantly make that mental connection.
Exactly. But an ML algorithm requires all of those signals to be perfectly aligned in a single wide row to calculate probabilities and find patterns.
And that resulting wide table, that's your feature matrix.
That is your feature matrix.
Okay, so we've built this massive wide feature matrix conceptually, but the database engine is completely blind, right? It doesn't inherently know that user 101 in the profile table is the exact same entity as user 101 in the checkout log.
No, it has no idea. To the database, it's just looking at isolated buckets of data.
So how do you force it to make that connection?
You force the connection through join keys. A join one combines rows from multiple tables by looking for a common identifier that exists in both places.
Like a user ID.
Exactly. The most common example is a user ID. If you want to merge a user's profile info with their purchase history, you just instruct the SQL engine to match users.userid to orders.userid. That key acts as the bridge. But, and this is a huge but, this brings us to a critical engineering trap that just quietly destroys data pipelines all the time. The data types of those keys must match perfectly.
Okay, let's unpack this. Wait, so even if the ID is the exact same number, like 101, if the computer thinks one is math and the other is a word, the whole reality we are trying to rebuild just breaks.
It absolutely shatters.
But doesn't the database see that a 101 is a 101?
It absolutely does not see them as the same thing. And the mechanism behind this is so crucial to understand. Under the hood, when you execute a join, the SQL execution engine is often trying to build a hash table in its memory to match these keys at really high speeds.
Okay.
So it takes the key from the first table, runs it through a mathematical function, and stores it at a specific memory address.
Right, so if users.userid is stored as an integer, like a binary number optimized for math, the hash function outputs one specific memory address.
Exactly. But if orders.userid is stored as a string, which is just an array of characters mapped to a text encoding like UTF-8, the hash function for that text array yields a completely different memory address.
Oh, wow, so it's looking in the wrong place entirely.
Yes. The database engine compares the two addresses, sees no match, and just quietly drops your data.
That is wild. Imagine you're an engineer deploying a new prediction model. You write your query, the code executes without throwing a single error.
Not one error.
But suddenly your predictions are absolute garbage. You dig into the matrix and realize your entire data set is empty or just scrambled because of a formatting technicality.
It happens all the time in the industry. To the database engine, the integer 101 and the text string 101 are fundamentally different entities in the universe. Professional ML engineers never assume keys will just magically align.
They explicitly verify data type consistency.
Always. Sometimes casting the data to force a match before they ever attempt to rebuild their datasets. It's a mandatory sanity check.
Okay, so assuming you run that sanity check, your keys actually match and the hashes line up. You command the database to build the bridge, but the database still needs rules of engagement, right?
It does.
From our source material, the engineer has to choose exactly how to combine the tables, and this choice basically dictates who survives the process and who gets deleted from reality entirely.
That's exactly it. Once the keys match, you have to choose your join type. And the two fundamental architectures you'll use are the inner join and the left join.
Okay, break those down for us.
So an inner join is incredibly strict. It only keeps matching rows.
Meaning,
if a user exists in your base users table, but they have absolutely no records in the orders table, an inner join completely removes that user from the final resulting data set.
they just vanish from the model's worldview.
Completely erased. Just gone. A left join, on the other hand, preserves the base population.
And left just refers to the first table you write in your query, right?
Exactly, which is usually your base table of users. With a left join, all users remain in the data set, even if they have 0 matching orders in that second table.
So for machine learning pipelines, the left join has to be the default choice.
It is the undisputed default choice. When you build a model, you always start by defining your population of interest in the base table.
Say your goal is to predict which registered users will buy a product next week.
Right, so your base table is all registered users. You then use a left join to attach behavioral features to that fixed population.
I feel like a lot of people might be tempted to just write an inner join there because, I don't know, it feels cleaner to only look at people who actually did something.
Oh, it's a huge temptation.
But think about what that actually means. Using an inner join in that scenario is like trying to study customer behavior, but intentionally walking over to the filing cabinet and throwing away the files of anyone who browsed your store but didn't buy anything.
It's absurd when you put it like that.
To build a smart model, you have to study the non-buyers too.
You absolutely do. And the fallout from throwing those files away is massive. What you just described is called accidental bias or selection bias.
Can you give an example of how that plays out?
Sure. Let's say a subscription box startup wants to predict who will upgrade to their premium tier. The junior engineer uses an inner join between the users table and the premium upgrades table to gather feature data.
Okay, makes sense so far.
But because of the inner join, the resulting training dataset only contains people who eventually upgraded. The ML model looks at this data and learns a very simple, catastrophic lesson.
Oh.
100% of humans who use this app upgrade to premium.
Oh no, so the startup launches a massive ad campaign based on this model, assuming every new user is a guaranteed premium subscriber.
Exactly. They bleed millions of dollars in customer acquisition costs because the model was utterly blind to the concept of churn.
Wow.
An innocent, seemingly logical SQL query fundamentally ruined the model's understanding of reality.
It trained on a completely distorted worldview where failure simply does not exist. That is a terrifying amount of power for one SQL keyword to hold.
It really is.
But this brings up a practical friction point. Here's where it gets really interesting. If you use a left join to keep those users who never bought anything, what actually happens to the columns that were supposed to hold their order amounts?
Ah, that's the big question.
Because we stapled those columns onto the wide feature matrix, the columns are literally there, but the data doesn't exist for those non-buyers.
Right. So when a left join forces a row to exist just to preserve the base population, but there's no matching data in the join table. The database fills those empty spaces with NOL values.
Okay.
So user 102, who browsed but never bought anything, will have a total spent value of NOL.
Which sounds like an error to a lot of programmers.
Exactly. This is where you have to shift your mindset from traditional software engineering to machine learning engineering. To a software developer, an NOL is a nightmare.
Right. It means a missing value, a broken form, or like a null pointer exception that just crashes the whole application.
Exactly. But in the context of building a feature matrix, NUL is not missing information. It is a highly powerful feature signal.
Because the literal absence of data is actually a definitive piece of data.
Yes.
It tells the model, in absolute terms, this person took 0 action.
Exactly. An NLN of the total spending column explicitly signals the behavior of a non-purchaser. If you use an inner join, that user would be gone, and the model would never learn what the behavioral footprint of a non-purchaser even looks like.
That makes so much sense.
By using a left join and really embracing those NLL values, you feed the model the explicit signal of non-behavior.
And then down the line in your pipeline, you'll probably write some Python code to impute those NLLs, right?
Yeah.
Like maybe replacing them with zeros before the final training step.
Exactly. You handle it in Python later. But the critical victory is that you captured the reality of the situation at the database level. You preserve the fact that this person did not buy.
So the left join is really the hero of feature engineering. It keeps your population intact, it prevents accidental bias, and it highlights non-action through NYELs.
It's the MVP.
You run your left join, you get your matrix, you feel like an engineering genius. But looking at the architecture notes in our sources, there is a hidden trap waiting when one user interacts with multiple things.
Oh yes, the fan-out problem.
Right, the fan-out problem.
Yeah.
If I am joining a single user to their order history, where exactly does the fan-out happen?
This is arguably one of the most destructive mechanical mistakes you can make in SQL for machine learning.
Okay, walk us through it.
Let's visualize the memory state of the tables. Your base users table has exactly one row per user. User 101 is a 23-year-old from New York. That is one distinct observation.
Right.
But your orders table has multiple rows for user 101 because that user made, let's say, 3 separate purchases over the last month.
Okay, so 3 rows over there, 1 row here.
Right. When you tell the database to left join the users table to the orders table based on the user ID, the SQL engine executes a Cartesian-like match for those specific keys. It has to match that single user profile row to all 3 order rows.
Wait, so if I don't aggregate first, my machine learning model will literally be tricked into thinking I have 3 identical 23-year-old users instead of just one highly active 23-year-old. Does the database just randomly pick one of the orders to attach, or does the query crash?
Neither. It does something much more insidious. It duplicates the user.
Oh, no.
The database engine creates a new row for every single match it finds. Your resulting feature matrix will suddenly have 3 separate rows for user 101. The matrix fans out and becomes exponentially larger than your actual base population.
And the danger there is just massive.
It cannot be overstated. By duplicating the user, you duplicate all of their base features. The model now literally sees 3 23-year-olds from New York.
Which gives highly active users unfair heavyweight during the training phase.
Exactly. And even worse, it completely breaks the fundamental statistical assumption of machine learning, that each row in your dataset is an independent observation.
Because they aren't independent. It's just the same person wearing a fake mustache, standing in line 3 times.
That's a great visual, yes.
The model looks at the data and thinks your app is incredibly popular with a massive diverse crowd of 23-year-olds, when in reality it's just one highly active person buying a lot of stuff. The whole premise of the prediction algorithm is compromised.
Totally compromised.
So how do you fix this? Do you just filter out the duplicates later in Python?
No. Filtering later in Python is highly inefficient and really dangerous because you've already lost the historical context of those extra orders. You don't know which one was first or how much the total was.
So what's the correct approach?
The correct architectural approach is a 2-step process. You must aggregate before joining. You do not join the raw, row-by-row event data directly to your base users.
Okay, so what does that look like in SQL?
You use a mechanism like a common table expression, or a CTE. You basically create a virtual intermediate table. Before the database even looks at your users table, you instruct it to cordon off the orders table.
Just isolate it.
Right. You write a query to group E by the user ID, and you calculate the SU of their order amounts, or maybe the count of their total orders.
Oh, I see. You are forcing the database to compress all those individual actions. You roll all three of their past transactions up into one neat little summary package.
Exactly. You reduce the complex event data down so that it matches the granularity of your base table, which is exactly one row per user.
Nice.
This virtual table now has one row for user 101 with a calculated column for total spent.
And then you join it.
Then, and only then, you execute your left join. You join that single aggregated row back to your base users table.
So now, user 101 remains a single row in your wide feature matrix, but they have a clean, newly minted column showing their total lifetime spent.
Yes. No duplication, no fan-out. And your statistical assumption of independent observations remains perfectly intact.
That is brilliant. Let's zoom out and summarize this framework, because the mental model here is really what separates a beginner from an industry-ready engineer.
Absolutely.
We start with the reality that database architecture shatters information for storage efficiency. The pipeline you build to reconstruct that reality flows in a very specific logical sequence.
Yep, it's a step-by-step process.
You take your base tables, which define your exact population of interest.
Yeah.
You take your event tables, like orders, clicks, or sessions, and you aggregate them into summary features so you don't break the space-time continuum with duplicates.
Love that. Yes.
Then you use the JIN, specifically the left join, to snack those summarized features onto your base population, and the resulting flat, wide 2D tensor is your feature matrix.
That's the formula.
The JIN is really the gatekeeper of your model's reality. It dictates data completeness, it decides who stays, who goes, and what behavioral signals are available for the machine learning model to actually study.
The join is the crucial execution step, where fragmented data finally becomes connected context. It is the exact moment where reality is rebuilt.
Well said. Now you know how to select columns, filter rows, and combine tables without destroying your dataset in the process. But the next logical hurdle is the aggregation step itself. We briefly touched on summing up purchase amounts, but behavior is vastly more complex than just a dollar total.
Oh, definitely.
How do you capture the nuance of a user's journey? In our next lecture, we will cover how events become features aggregating behavior SQL for ML Engineers L5.
But before we wrap up, I want to leave you with a provocative thought, a problem that engineers wrestle with at the highest levels.
Oh, lay it on us.
We've established that joins allow you to reconstruct reality by snapping pieces back together based on a common key like a user ID. But what happens when that reality changes over time?
Oh, that's tricky.
Think about the mechanics of this.
Mm-hmm.
How do you connect data when an order happens today, but the user's profile information, like their location or their subscription tier, changes tomorrow?
Right, because the database just overwrites the old data.
Exactly. If you just blindly join everything based on the ID, you might accidentally attach tomorrow's profile data to yesterday's behavior. You end up allowing the model to peek into the future, basically predicting a past event using future information.
That is mind-bending.
So I really encourage you to keep an eye out for how the dimension of time will eventually challenge and complicate this newly rebuilt reality.
That temporal trap data leakage is a whole different puzzle to solve, and it proves why you have to deeply understand the mechanics of your queries, not just the syntax. Keep practicing your table aggregations, watch out for the fan-out trap, and we'll see you in the next deep dive.